In this example, we'll be going over how to use the array cluster channel. This channel is used to represent the Salley-Valenzuela channel model, or the spatially sparse channel model, commonly used for millimeter wave communication, but in general it's a simple geometric-based channel model where the summation of many arrays stemming from multiple clusters create the channel. So if you look at this first line here, we create a array cluster channel by simply writing channel.create and using the array cluster specifier. Like other channels, we'll need to do the necessary initial setup, including setting the propagation velocity. In this case, we've set it to the typical 3e to the 8. We also set the carrier frequency, in this case to 2.4 gigahertz. And then, like other channels, we set the transmit and receive arrays. In this case, we've set them to two uniform planar arrays. In this case, the transmitter as an 8x8 array, the receiver as a 4x4. And we set those using the set array functions of the channel. Then we have the option, like before, to force the channel matrix to be normalized to a certain energy. We can, of course, comment this out if we don't need it. But in this case, just for the sake of a demonstration, we'll include it. And then the arrays that make up the channel, which if we go to the MFM website, we can see here, the channel is a matrix, or is a summation of rank 1 matrices, where each rank 1 matrix is captured by this outer product of the array responses of the transmit and receive arrays, and then they're multiplied by some complex gain beta at for each array. And then this is summed over each of the arrays within each cluster. So by this model, there is a fixed number of arrays per cluster, so each cluster is assumed to have the same number of arrays, and then you can have multiple clusters that make up the channel. So there are a few different parameters here, and how they're drawn, what distribution they're drawn from, can vary just depending on the setting or how the user wants to configure it. For example, the AODs and AOAs, the angles of departure and angle of arrival, may be drawn from some distribution, and then similarly the gain of each ray, beta, may be drawn from some other distribution. It's common for beta to be drawn from complex normal distribution, and then these angles, they vary with how the user wants to model their behavior. So this is how the matrix, the H matrix, the channel matrix, is constructed. Of course, this is a frequency flat case. There is a frequency selective extension to this model if you look up frequency selective millimeter wave literature. Okay, so yes, like before, this contains the typical properties of other channel objects in addition to some other specific parameters for this model. So the number of clusters, as we mentioned before, and the number of arrays per cluster need to be defined, and then the distributions of which the AODs and AOAs take, along with the array gains, need to be set. So if we go back to MATLAB and we look here, we can see that in this case the array gains, beta, those are drawn from the complex Gaussian, so a complex normal distribution, by the C-Gauss specifier. We can also set them to have unit magnitude, so each one has magnitude 1, a gain of 1, just for the sake of convenience, or if you're wanting to test different things out, you can use this unit. But those are currently the only two options available. And then we can set the ray gain distribution by this set ray gain distribution function. Similarly, we can set the angle of the rays. So the cluster angles, so the mean of the rays within a cluster, those are drawn uniformly over their range, which we'll see in a second, but the actual arrays within each cluster are drawn, they can be drawn a few different ways. Currently, with this setting, they are set to be distributed Laplacian around the mean with a azimuth standard deviation and elevation standard deviation. We can also use a Gaussian, so in this case it's a real Gaussian, in both azimuth and elevation. This is the variance. And like I said, these are the rays within each cluster. So for a given cluster, they're Laplacian distributed with a certain mean and these statistical parameters. Now the cluster angles of arrival and angles of departure are set uniformly in MFM currently based on the bounds we define here. So in this case, we have an azimuth min, an azimuth max, an elevation min, and an elevation max for the AOD. So you can see this is the cluster AODs are drawn uniformly on this range, and then all the rays within those will also be required to fall within this range too. But the actual cluster AODs are drawn uniformly on this range. Okay, and then this step is repeated with the AOAs. We can also define a maximum and minimum number of clusters. So if the number of clusters in the channel is variable, so if it's randomly drawn, MFM supports a uniformly drawn on this range. The number of clusters will be drawn somewhere between 1 and 10 in this case. And then similarly, the number of rays per cluster will also be drawn uniformly on whatever range is specified here. And then we can invoke a realization just like all other channels using the realization function, which returns channel matrix H. And then for this particular channel, it's useful to view the beam space. So we'll see what that looks like whenever we run this script. So if we go ahead and run this, let's go ahead and hide those beam spaces and just look at the channel itself. This is the channel that we've created, and you can see in this realization it's generated 9 clusters. Remember, our range was 1 to 10. It's generated 5 rays per cluster as its random variable here. So we also had it to be drawn on the range 1 to 10, and in this case it was drawn 5. So there's going to be a total of 45 different rays in this channel. So there will be 9 clusters, each having 5 rays per cluster. Okay. It also has drawn cluster AODs and cluster AOAs, which are the means, as we mentioned before, that all the rays within each cluster will take. So if we look at that, we could see C.cluster AOD, and this lists azimuth and elevation angles of the 9 different clusters. So this will be this will be the mean of the rays of the distribution of the rays in that cluster. So then the actual AODs that are realized for each ray are stored in AOD and AOA. So as you can see, there are 9 clusters, there are 5 rays per cluster, and then there's an azimuth and elevation here. Okay, we also have the transmit and receive array. You can see it's automatically populated the number of antennas at the transmitter and receiver. Remember, this was an 8x8 transmit antenna, a 4x4 receive antenna. And then the channel matrix, which has also been populated, is of size 16 by 64 accordingly. And then we have our other typical channel settings. So if we go back and we look at those figures that it created, we can see in this case we have the azimuth beam space figure. So the azimuth angle of departure is on the x-axis, and the azimuth angle of arrival is on the y-axis, and you can see these are our different rays in the channel. So there are, recall, 9 clusters. So if I had to guess, it looks like there's 1 here, maybe 2 here. There's 4, 5, 6, 7, 8, 9, it looks like. So there's our 9 clusters. And the brightness, so brighter rays correspond to stronger rays. Remember, those were distributed according to a complex normal distribution. So the magnitude corresponds to the color of the rays. So we have that in azimuth as well as elevation. And if we perform another realization, if we run this again, we'll get different results. And so you can see here's another result, and we can see how many. In this case, there were 10 clusters generated with 7 rays per cluster. So you can see that if we invoke this realization each time and look at look at the channel object again, we can see that a new realization is completely generated just with one line of code. So all a user needs to do, for example, for Monte Carlo simulations, is simply place this c.realization within a for loop with all of this being fixed, because all the stochastics of the actual channel are captured by the channel object, and then realization will simply realize a new instance of the channel. Okay, so this concludes the channel or the array cluster channel object. For more information, please visit the MFM website and stay tuned for more videos. Thank you very much.